works. Okay, what do we got next? Number of electrons. How many electrons did it have? 36, right? Why? Because there is no charge written in the top right-hand corner. If there was something written there, you'd have to deal with that. But there's no charge written there. Now, how many, what's 80 minus 36? 44. All right. So we are good with that, right? Now, everything has what are called isotopes. Let's do them. Let's do a U-235. And let's do a U-238. Okay. So, let's see what the difference between U-235 and U-238 is. Well, how many protons we got here with U? It's not on here. It's how many? 92, right? It's on your periodic table, 92. And that also means we got 92 electrons. Now what about here? How many protons we got here? 92. How about over here? Okay, now let's do some subtraction. What is 235 minus 92? 143. So what's the difference in U-235 and U-238? One's heavier than the other. Okay? Why is one heavier than the other? Because it has a different number of neutrons in it. These things right here are called isotopes. Iso means the same. That means that everything is the same except the number of neutrons. Now the number of neutrons is a pretty interesting story in itself because as the number of neutrons change, it can make a nucleus be what the nuclear chemists call as magic. It can have a magic numbers. And what that means is it will allow something to be radioactive versus something to not be radioactive. Okay? So the number of neutrons can cause different properties in radioactivity. Generally, though, they do not cause different properties in reactivity. Okay? Because the chemistry of uranium-235 and the chemistry of uranium-238 are similar. I did not tell you the physics was the same. I didn't tell you that nuclear properties were the same. I said the chemical properties are the same. Those three neutrons generally don't matter. Why? Because most of the time, chemistry happens where? In electrons. We've got the same number of electrons. Now there is one example I can think of, and that's with hydrogen. If you've got different isotopes of hydrogen, sometimes you can have a deuterium effect where kinetics of reactions can change and so forth. But with hydrogen, if you just add one extra neutron, you've doubled the mass of the atom. Now how many neutrons would you have to add here to double the mass of the atom? 143. That ain't no way. All right, it's just too much. All right, are we good? Now, let's talk about the common, I don't know about the common, but the simplest isotopes. Maybe we should have did that to start with. I don't know why we didn't. The simplest isotope up there is something called H1. That's called protium. That right there is what they call your garden variety hydrogen. All right, hydrogen is located all in your body, in outer space, and the planets, water, it doesn't matter. It is common. Okay? And if you was to get eyeball to eyeball with any type of hydrogen, your garden variety hydrogen would be this right here. How many protons does that have? One. So, one proton, one electron, how many neutrons? 0. Okay? Again, that is your garden variety, 99.9% type of hydrogen. Now there's another type of hydrogen out there that's called H2, and the name for this one is called deuterium. All right? So, how many protons does it have? No, protons.
Oh.
1. How many electrons? And how many neutrons? So what is the difference between protium and deuterium? 1 neutron. Okay. Now, you remember I told you how chemistry really didn't matter? Well, it does here. Because like I say, if you look at the mass of this one and the mass of this, double. All right, so chemistry can be affected there. And there's another one called tritium. All right, or tritium. Has anyone ever heard of tritium? All right, that's not necessarily a naturally occurring guy, and that's H3. Well, what's going on here? Well, there's 1 proton, 1 electron, and now 2 neutrons. So they're getting heavier and heavier and heavier. All right. Now, maybe we should stop there for just a moment and give a little bit of an historical reason behind these things. So what kicked this off? And before I ask what kicked it off, maybe I can ask you this. What are we using today that has to do with radioactivity, that has to do with isotopes? Does anybody know?
Carbon dating.
Carbon dating. Wonderful. That's got to do with it, right? You can carbon date something only up to so many years. Okay? Now, after so many years, you can use something that's called argon dating. And you can start dating geological things from way back a long time ago. Okay? What else have we got that's come out of atomic structure? What about a PET scan? You guys know what a PET scan is? It's called a positron emission tomography. And that is when you can take a radioactive dye that emits a positron. Now this right here will mess you up, and later on maybe it'll make you want to study science, who knows. But if you have a positron emission, do you guys know what a positron is? No? It is an electron. It is an electron that's positively charged. It's what's called the antimatter of an electron. All right, and when a matter and an antimatter see each other and they collide, they will just disappear. All right. Okay, so that positron is radioactivity that comes out. So you take the liquid, they put it in your veins, whatever. And the idea is if you have a tumor or some abnormality or what have you, that the radioactivity will go to that tumor. Start being radioactive. They can put you underneath a scanner, and then they can pick up the radioactivity. All right. Now, what's the idea? The idea is, as used to, they would have to put you on the operating table, slice you open, get in there, and explore. So the surgeon could put his eyeballs on it, see what he's dealing with, and in some cases sew you back up, and then bring you in later for another operation once he finds out what's going on. All right. Now this is a non-invasive type diagnostic tool that they can use to try to test for things without putting you through a lot of drama. Okay, so that's something that's came out of the radioactivity and so forth. All right, a lot of your imaging techniques, X-rays, all of that stuff has come out of studying this atomic structure. Now, where did all that come from? Well, all that came from World War II. All right, in the years leading up to it. It turns out that, as always with our federal government, if you want something funded, you need to attach the word defense next to it. Okay, and that's exactly what they did. Is there were some